Hello, welcome back. We are nearing to the final few classes of this course, and that is metals in biology. We are trying to summarize little bit quickly so that you can study these for exam purpose relatively easily. What we have seen in case of the iron oxygen intermediates, that they are very capable of doing oxygenation chemistry. Some of them are oxygenases, some of them are oxidases, right. But more importantly, almost every organic substrate can be functionalized by utilizing the iron oxygen chemistry. This chemistry can be between the two iron center, between the oxo species is bridged in between, or it could be as fascinating as those the terminal oxo species or these porphyrin oxo based species. There are non-heme oxo based species as you have also seen, but these species are also known to be very effective. So, you have seen these many different types of reaction: hydroxylation, oxidative ligand transfer, desaturation, cyclization, electrophilic aromatic substitution, and cis dihydroxylation reaction. All these reactions you are hopefully now familiar with. Most of them are going via the radical mechanism, as you can see in there. This one where arene activation is involved or arene oxygenation is involved, it is going through an electrophilic aromatic substitution reaction. The cis dihydroxylation can be mediated by this oxohydroxy species to form this from this extremely exciting products. All these cases this is this oxo radical formation and corresponding the CH bond activation and the radical formation is key, and that is what we have seen over the many different high valent iron oxo intermediate cases. One of the exciting species you perhaps would remember as well, that the alpha ketoglutarate dependent enzyme are capable of doing both the oxygenation chemistry as well as the halogenation chemistry, depending on the slight changes they have in their coordination motif, but nonetheless they will be having this alpha ketoglutarate as an internal substrate for their activity. So, what you have seen earlier with the alpha ketoglutarate dependent enzyme is simply it binds with the non-heme iron center, and oxygen activation that takes place at the iron center. Before that the substrate will orient itself, get it ready, get set go, and then oxygen will start gets activated at the iron center. It first form a iron 3 superoxo, which immediately is trapped or attacking the keto moiety of the alpha ketoglutarate. The alpha keto center is getting reacted with forming an alkyl peroxide like intermediate, which can then undergo oxygen bond cleavage to give rise to these iron 4 oxo species. These are reactive intermediate and the substrate is sitting right close to it, therefore the oxo will obstruct hydrogen atom to form the hydroxo and the R radical, right. This R radical and hydroxy radical can combine with each other to give the ROH. Once again this water molecule goes out, alpha ketoglutarate comes in, RH takes its position, gets set perfectly, oxygen comes in, forms the iron 3 superoxo, iron 2 plus was there, it forms iron 3 plus, it forms the superoxo. This superoxo attack the alpha keto center to form this cyclic nice intermediate, where it is now iron 4 thanks to the nucleophilic attack on this keto center, which is then getting O minus by transferring 1 electron from the iron center, oxidizing is to iron 4 plus from iron 3 plus, right. Now this iron 4 plus alkyl peroxo type of intermediate can undergo the oxygen bond cleavage, whatever way you want to see it, with the simultaneous expulsion of the CO2 moiety. It gives rise to the succinate bind the iron 4 oxo intermediate, which is the real active species for abstracting hydrogen atom from the sp3ch bond right over here. This is nothing but, you can see that iron 3 O dot, this O dot and this RH will form the bond or form this iron 3 OH bond, and R dot radical will be generated during the process. So, I am sure you are having clear understanding among these different OH and O bond. For instance, if you have seen earlier this cupril species, for example. So, we are saying that cupril is nothing but Cu2O dot. This is exactly same as Cu3 double bond O, because this will give electron, that will give electron to form that. Similarly, for example, if we are talking about iron 4 oxo species, this is also nothing but going to be iron 3, these are same species, in different form one can write iron 3 O dot. Now, this, as you have seen in the last slide, these iron 4 oxo was reacting with RH, okay, to give you what? To give you iron 3 OH. How that is happening? Because this iron 4 oxo is nothing but iron 3 O dot, and if you are giving RH to this is forming R dot, this is forming H dot, and these two bonds. So, overall you get iron 3 OH plus R dot. Hopefully this is clear. On the other hand, over here if you want to draw, it is nothing but this bond is breaking, and then that is giving, and that is forming the R dot. So, that is R dot. In any case, whether you want to think that iron 4 oxo is a double bond O iron, or it is a iron 3 O dot, all leads to the exactly same product, iron 3 hydroxo R dot, iron 3 hydroxo R dot. So, this is the pattern of the radical formation. You can say the same thing for a copper oxo intermediate or a iron 4 oxo intermediate, although these species in a cupril species in the enzymatic setup, although proposed, are still doubtful in the synthetic setup. Recently some evidences are coming, but still one need to further develop this chemistry in the synthetic setup, so that their relevant can be understood in enzymatic setup. Okay. So, overall I hope you are able to understand this mechanism. So, you are forming the succinate from this alpha ketoglutarate, you are getting rid of this carbon dioxide moiety from here, and I hope you understood that how it is attacking over there, and this is O minus is forming, and then this O minus overall is get oxidizing, or so overall oxidizing iron 3 plus. Let me draw that step again. So, this is here a oxygen radical is attacking a keto center. Now, this keto center over there will form a radical, overall it would be forming OOCO, let us say these are oxygen labeled, maybe it would be easier to understand. So, that is there, these are there, this is iron center. Now, this, so I am redrawing that over here. So, this is now attacking, and these keto moieties are drawn over there. This oxygen iron is giving rise to a carbon center and O dot, right. This is iron 3 plus, this is remain iron 3 plus, and then this iron 3 plus transfer one electron from here to give to oxygen, which becomes iron 4 and O minus. That is what I am trying to explain. Hope the electron transfer does not throw you off too much, and you can count these electrons stepwise without much of a problem. Let me draw that one more time very clearly for you, and that is very simple process. I hope it is not getting complicated for you. So, you start with iron 3 superoxo, iron 3 superoxo. Okay, you have a keto center attached with you. This is the one which is going to form the carbon dioxide. In any case, I am not drawing the rest of it. So, this intermediate goes on to attack this center, right. So, this pi bond will cleave to give you this oxygen iron 3, the remaining part remain constant, right. So, that is what you see, right. So, this is what you see along with the O bond, O dot over there. So, this O dot over there is attacking and forming this radical and that radical forming in this bond, right. This is the new bond form and this is the radical that is coming over there. This radical and then pick up one more electron from this iron 3 overall to give you this center as iron 4, and this oxygen becomes O minus along with formation of this alkyl peroxo intermediate, right. I hope you got it correct without any trouble in understanding, right. So, this radical attack at this carbon center and that oxygen radical form one electron transfer from that center to give rise to iron 4 and this carboxylate. Anyway, let us move on. What we have seen that this alpha ketoglutarate can form iron oxo intermediate very interestingly and very simply, then that can go on to react with the substrate to give you the substrate hydroxylation product. The twist here is if you do not have that 2 histidine 1 carboxylate intermediate, 2 histidine and 1 aspartate intermediate, the facial triad, the facial triad, so called facial triad intermediate, if you do not have 2 histidine and 1 aspartate, these 3 moiety if you do not have, then you are in for a quite exciting part, and that is just 2 histidine and 1 X, the halogen. So, this was aspartate in the last case, now this is halogen. This halogen will then be reactive with the radical center that is getting generated at iron. For instance, if you are bringing the alpha ketoglutarate, of course alpha ketoglutarate in, substrate is sitting right over there, iron 2 center is there, reacts with oxygen, binds with it and then form the iron 3 superoxo intermediate, iron 3 superoxo intermediate, right. Iron 3 superoxo intermediate, then that attack on the carbonyl center of this and subsequently it form the iron 4 oxo with the succinate. This is upon decarboxylation of this alpha ketoglutarate unit. Now, this iron 4 oxo unit, as you can see over here, iron 4 oxo unit over here then can abstract hydrogen atom just like what you have seen in the hydroxylation chemistry, but only difference is you have the halogen over there. Now, it can abstract hydrogen atom from the substrate to give the substrate radical intermediate along with the formation of OH. Now, there is a competition between X and OH where OH loses because this radical is close to this X, and more importantly the reduction potential is helping out as well. Overall, this X selectively transfer over there, no hydroxylated product is found. So, RCH2X is formed, in this case RCH2Cl is formed if X equals chloride, and if you have other things not present or you have difficulties, then hydroxylation product may be formed. So, these alpha ketoglutarate dependent enzymes are, I guess, quite exciting. Not only they are capable of doing the hydroxylation chemistry, they can also do the halogenation chemistry, right. We have seen that as well. So, what we have seen so far that not only reversible dioxygen binding, oxygen activation is also fascinating, right, and more fascinating I would say, and more challenging, more opportunities and more substrate scope can be involved. Iron porphyrin cytochrome P450 chemistry we have discussed already and summarized it. Dicopper center tyrosinase also we have discussed. We have discussed in the last few classes about MMOs. I will briefly mention these again. So, the main reaction we are trying to study is in case of MMO, these are going to be a non-heme iron center. Once again, do not mix between the heme and non-heme iron center. These are going to be the non-heme iron center. Methane is going to be converted into methanol with the help of the oxygen. If you are having the leveled oxygen, this is going to be leveled over there, right, that is correct. So, these are fascinating enzyme, as you have seen there are going to be 2 iron center, and these both the iron centers are quite exciting over there. These are unsymmetrical, as you see the coordination environment around this site is completely different compared to that one, which is quite fascinating. You have one glutamate here, you have two glutamate over there, right. Now if you have seen the earlier mechanism, once again the oxygen comes into the picture, and earlier mechanism suggests that this oxygen will follow up all the way through to first of all transfer one electron from here and one electron from there to form the superoxo intermediate. This superoxo intermediate can again transfer one electron from there to give you the iron 3 2 minus. This is the peroxo intermediate. From there on this oxygen bond can be cleaved to give you the bis mu-oxo, where oxides are O2 minus, iron 4 and iron 4. It was iron 3. This oxygen bond cleavage gives you iron 4 2 minus. Now the methanol comes and react with this Q intermediate. This is the intermediate Q, which is responsible for the methane activation to give you the methanol product. There is a slight change or the revised mechanism subsequently. This revised mechanism tells that this iron 4 oxo or iron 4 dioxo intermediate will be capable of forming a new intermediate. Perhaps as you have seen, this new intermediate is going to be iron 4 hydroxo oxo iron 3 intermediate, although further characterizing this intermediate is not that very easy, but more importantly I believe that this peroxo intermediate can also be reacting with the methane substrate to give you the methanol along with the formation of diiron 3 dihydroxo intermediate. This peroxo and this bis mu-oxo, this is bis mu-oxo intermediates are quite exciting intermediate for this species. As we have noticed there that these intermediates are quite exciting. If you are following overall, following up to here, this is a 30 milliseconds, right, 30 millisecond time frame. If you are following overall from here to here, this is a 500 millisecond time frame, right. So this is forming, this intermediate is forming if you are following for 30 millisecond. If you are mixing oxygen with this reduced species within 30 millisecond or right at 30 millisecond, you can follow up this one, what happens to this, what is the decomposition product, and this has a characteristic band around 720 nanometer. If you are mixing these species with oxygen and waiting for 500 millisecond, this one you form, and this is having a very characteristic band at 420 nanometer, right. These species are the one you can follow and then react it with methanol, methane to give the methanol product, right. So overall what you have seen previously is the decay of these say 420 peak or 720 peak can be rationalized, can be followed quite easily to give the detailed kinetic studies. The detailed studies shows that it is actually more exciting than what we thought. Q, the intermediate Q, as you have seen, the bis mu-oxo intermediate can react with methane to give you a bond making and bond forming step over here, where we have seen an oxo-hydroxo species is generated. This oxo-hydroxo intermediate can either go through a radical intermediate or through a concerted intermediate. Concerted intermediate is more challenging or more energy demanding, therefore we end up getting a more preferred pathway where this radical species are formed. Upon this hydroxo electron rearrangement, we get hydroxo radical. This hydroxo radical and the CH3 radical combines to give you the product. Of course, the alternative pathway is little bit more energy demanding, therefore you do not perhaps follow this intermediate that very clearly, right. So this is a quick summary for these methane monooxygenases. You have seen also two types of substrate over there. One substrate is the methane and corresponding other substrate which will have the very high kinetic isotope effect, right. So these are having very high kinetic isotope effect, as you can see over here. These highlighted ones right now are known as the class 1 substrate, where methane approach could be interesting and simple, but more importantly the CH activation is the rate limiting step. So, the diffusion of methane towards this Q intermediate. So, if you are looking at the Q intermediate, which is nothing but iron 4 oxo iron 4 intermediate, this intermediate is approach of this with respect to this CH4 is very simple, nothing, no problem happens over there, and this approach, overall approach of CH4 with respect to bis mu oxo is not the rate limiting, but this activation of this bond is rate limiting for this case of CH4 and CD4. And similarly, as you have seen in case of acetonitrile and in case of nitromethane, this approach is not problematic, but CH activation is the most damaging or most difficult step. On the other hand, for the substrate like this ethane and the methanol, this approach of this substrate towards this active site is the one which is critical or most challenging, and therefore we will end up getting the diffusion control process. If you are remembering the previous drawing carefully, you will note that for methane, this is the black curve, this path is the diffusion of methane towards the iron 4 oxo species is not really problematic. So, this diffusion or pre-orientation of the methane is happening quite easily, this can happen quite easily, but this is not so easy if you have approach of ethane, and that is how the substrate specificity perhaps is obtained. See, this is the same intermediate as this, but if you have H2 CH2, that means CH2H, that means the ethane, this approach of this into towards this is not that very easy, and this diffusion control is becoming, or diffusion step is becoming the rate determining step. As you can see from the methane case, this is not very high, or alternatively, but the other step, that is the CH activation step, is much bigger and much stronger. More importantly, for methane, bond dissociation energy is around 105 kcal per mole. For example, for ethane it would be 98 to 99 kcal per mole, which makes a huge difference, that CH bond dissociation becomes easier, and this is also perhaps one of the reasons why ethane CH activation will not be problematic one, but reorientation or approach of the substrate, diffusing the substrate with respect to the iron 4 oxo intermediate will be critical, as you see there. So, for the methane case, this is shorter, this is taller. For ethane case, this is taller, this is shorter. Okay. That is the summary from the MMO. So, the substrate dependent chemistry we have seen. Another exciting part we were seeing the 4 manganese 1 calcium cluster. I think the first thing that should come into mind, that these are microscopic rivers of the cytochrome C oxidase, which is heme copper oxidase, which is responsible for converting oxygen into water, but in the photosystem you are converting water into oxygen. And the crystal structure, as you have seen, the gigantic crystal structure have many caveats in it, many problem in it, but nonetheless this is the 4 calcium 1, 2, 3, 4 calcium 4 manganese center and 1 calcium center, that is over there. This can be redrawn like that, but although this crystal structure is known, but still this is completely questionable. The X-ray damage is the major reason why people do not believe that this is the structure for the oxygen evolving complex. So, what is the structure? Well, nobody knows still now. These are the major structure that is proposed and believed to be still active, but nonetheless, although some EXAPS data are there, but still people are debating on these. Some of these structure perhaps can be ruled out, but perhaps can still be existing in the discussion. But I think for time being we can, or for since this debate is still on, we cannot really rule out any of these structure completely, but these are the structure people believe are mainly happening. So, we have seen S0 oxidation state, we have seen S0 oxidation state, S0, S1, S2, S3 and S4 oxidation state. In each of the steps is oxidation happening, oxidation happening, oxidation happening, and in the final step oxygen bond formation is taking place. You have seen the oxidation state dilemma between these two. These species are still debatable, this is quite fixed, this is quite fixed, this is still debatable, and finally this is the fully oxidized form. There are multiple line spectrum in the EPR which is helping us in assigning some of those spectra. Always this simulation of this band as well as the experimental observation has to be quite critically done, otherwise the conclusion can be problematic. Different experimental studies are done to understand these intermediate in better respect or better clarity, but still their problem exists in these cases. The oxygen bond forming process, as you would imagine, that's the most important step, and that is the key point of discussion over here. Some believe that it is the calcium hydroxo, which is I think is quite reasonable, because calcium is the Lewis acid, it activates the water molecule to make its hydroxide, and this hydroxide and then can attack on this oxy center. But in other beliefs that calcium is not really part of, but anyway that debate for another day. This again calcium hydroxide, either this hydroxo can attack on this bridged manganese oxo or the terminal manganese oxo, still that is questionable. I think we can perhaps leave as it is. These questions are very difficult to solve at this point, and we can move on, because in the literature so far no clear understanding is obtained. Okay. So at the end what we have in the picture is, I think if anything you would like to remember, I think this is the case you should remember. These next two slides you should remember, although this is questionable, but still this is the thing you should remember. What is happening over here? The core over there, these center remain constant. Okay, this is one of the proposal, and this is something I believe is most likely closer to be the truth, but again nobody has seen the real active site. So what is happening over here is manganese aqua molecule is right over there, okay, and it is in manganese 2 plus. This is center is getting oxidized to manganese 2 to manganese 3, and then this manganese 3 is oxidized to manganese 4. Subsequently this manganese 3 aqua complex further gets oxidized to manganese 4 hydroxo, and finally to manganese 5 oxo, which is the real electrophile we are looking at, where calcium hydroxo can come and attack. If calcium hydroxo is attacking on this manganese 5 oxo, the oxygen bond is formed. I think job is done. Well, again this is remaining a question mark over there, but this is the one. If you have to remember anything for the manganese 4 calcium structure, because it is so complicated, you have to remember something to better understand it. There are caveats, there are problems, but I think this is something you should try to remember if the manganese 4 calcium oxo structure is drawn for the oxygen bond formation. I think this is the structure to be drawn. Okay, let us moving on. There is another exciting twist in this business, and that is the formation of the oxo radical from the tyrosine unit, which is proposed in some of the cases. In case of Blondin, that this is the oxyradical which is responsible for hydrogen atom abstraction for this manganese hydroxo species in S3. I think this is quite fascinating, most likely to be the truth or true, but who knows what is happening. But overall this phenol is forming, as you can see over here, and manganese 5 oxo is formed, and calcium hydroxo is nicely coupled with the manganese center, where this attack can take place and oxygen bond can be formed. Well, I hope you are able to make some sort of sense about this complex structure, but you can read always more. There are many references given, great chemical reviews and other reviews are available, and you are free to study all those. Please do understand that this remains still complicated, and many questions are still there which need to be addressed over the decades to come. Okay. With this, we will see you soon in the final few classes very soon. Okay. Thank you.